Okay, so we've been introduced to n-dimensional space, and we're considering a set of n coordinates, x1 to xn. And what we haven't said before is that it's important that these coordinates are independent, in the sense that the partial derivative of 1, so the ith coordinate with respect to the jth coordinate, is a Kronecker delta. So it's delta ij, which hopefully you'll know is 1 if I equals j, so if it's the same coordinate, and 0 otherwise. Okay, so this is a point. We can think about a curve. And curves in our n-dimensional space are defined in a parametric sense, where we have each of the coordinates is a function of some parameter u, and each coordinate has its own function, fi. So this is true for all I, 1 to n. Okay, so an example is a circle of radius r. So in our x and y coordinate, here our system has n equals 2, so it's two-dimensional, and our x1 and x2 are x and y. Okay, so here we have a circle which is defined as x1 equals x, and you'll know that we can parameterize the circle by the radius r, cosine some parameter u, okay, and u takes us around the circle. And x2 is y, and that's r sine u. Okay, so here our f1 is r cosine u, and our f2 is r sine u. So we can think about a second example. Let's say y equals some function g of x. Okay, so here our x1 again is x, and it's some parameter u. And our second coordinate, x2, is y, and that equals g of u. So going back here, our f1 is just u, and our f2 is this g. f2 is g of u. Okay, so we now come to an important part of the course, where we are going to discuss the transformation of coordinates. So we're considering some n-dimensional space, let's call it Vn. And we have a set of coordinates in this space, x superscript 1, x2 up to xn. We're going to be concerned with transformations of coordinates from this coordinate system to a different one. It's also an n-dimensional coordinate system, and let's call it x1 bar, x2 bar, up to xn bar. Okay, so we have two different set of n-dimensional coordinates. And we're interested in transformation of coordinates from the unbarred system to the barred system. So the transformation So the transformation that we're considering is defined by the new coordinates x bar, so the ith coordinate in this new system, is a function of all the old coordinates, x1, x2 to xn. Okay, and this is true for all I. And the transformations we will consider we call non-singular, and that means that the new coordinates are uniquely determined by the old coordinates. So there's only one function for each coordinate. Okay, so this function is unique. Okay, so here's an example. If we think about a 2D Cartesian system, x and y. Okay, so here our x1 is x, and our x2, our second coordinate, is y. And maybe we want to transform to a different coordinate system where we have some r and a theta. Okay, so we have polar coordinates. So here we have Cartesian, and here we have a polar coordinate system. So here, our new system we call x1 bar. That's the first coordinate in our new system. It's r, and our second coordinate, x2 bar, is theta. Okay, so we want to go from the xy system to the r theta system. And you know you can do this, so let's write our x1 bar, r, in terms of x and y. So the function here, this f, is just simply the square root of x squared, so our first coordinate, all squared, plus our second coordinate, all squared. Okay, so the radius here of, so the length of this line is just the square root of x plus y squared, x squared plus y squared. And our theta, which is our x2 bar, is just the inverse tan of y over x. So this is x2 over x1. Modulo pi, I guess. So for clarity, we'll just call this xi bar, a function of all the other coordinates. Okay, and it's important that for the transformations we consider that an inverse exists. So there exists an inverse transformation. So this inverse transformation describes the unbarred coordinates in terms of the barred coordinates. X bar 2, x bar n. And if we think about, say, a small change in this coordinate, dxi, then if we apply the chain rule, then this will be the partial derivative of that coordinate with respect to the barred coordinate, j, with a dxj. Okay, and we have to have a sum over all the j coordinates. Sorry, this is a bar. Okay, so a little change in this coordinate is given by the partial derivative of the unbarred coordinates with respect to the barred coordinates. So this is just the chain rule. And this quantity will be important to us. So it turns out that the inverse transformation only exists if what is called the Jacobian is non-zero. Okay, so we'll write the Jacobian now. Okay, so we're thinking about transformations from this unbarred coordinate system to the barred coordinate system, and also the inverse. Okay, and for this inverse to exist, so this inverse transformation, which we wrote as xi as a function of all the x bars, x1 bar, x2 bar, up to x bar n. For this inverse to exist, a necessary and sufficient condition okay, so the inverse transformation is defined by this thing. So a necessary and sufficient condition is that what we call the Jacobian is non-zero. J, which is the determinant of the Jacobian matrix. Okay, so this is the Jacobian. And J with the squiggle underneath is the Jacobian matrix. And the condition is that this is not zero, not equal to zero. So if this is true, if there is an inverse, then this must be true. And actually, the converse, that if this is non-zero and an inverse exists, for polynomial transformations, is one of the most famous unsolved problems in mathematics. It's called the Jacobi conjecture. So you can look that up on Wikipedia. If you can solve it, then you'll make a big name for yourself. Okay, so what we've got is a transformation from an unbarred set to a barred set. We're saying that we can go either way. So if there's a transformation from the unbarred to the barred, then we assume that there is an inverse from the barred to the unbarred. And for this inverse transformation to exist, this condition must be true. So we need to now talk about what this Jacobian actually is. Okay, so if we think about our inverse transformation, that's this guy. If we think about one of the coordinates, the ith coordinate, and let's think about a small change, dxi. So as we saw before, this is just given by the chain rule. It's the sum of all the unbarred coordinates with partial derivatives. So dxi by dx bar j dxj. Okay, so these are the coordinate differentials for the unbarred and the barred system. So this is true for every single I, so we can think about this as a vector of coordinate differentials. So dx1, dx2, down to dxn. And this is, we can think about it as a vector. It will be a matrix times the vector of the barred coordinate differentials. dx1 bar, dx2 bar, down to dx bar n. Okay, and this matrix has elements that are these partial derivatives of one coordinate with respect to the other coordinate in the different system. Okay, so the rows, let's call this dx by dx bar. And along the first row, we have the first coordinate, dx1. So dx1, dx1. And the columns are labeled by the number of the barred coordinates. So this is 1, this is dx bar 2 to dx bar n. Okay, so if we go down the rows, then we have, well, let me do the second one, just so it's clear. This is dx2 by dx bar 1. Okay, so we're changing the index on the unbarred coordinate as we go down the rows. And as we go across the columns, we're changing the index, so the superscript on the barred coordinate. Okay, so we can fill this in, and we have dxn by dx bar 1 to dx n by dx bar n. Okay, and this guy is the Jacobian matrix. And the elements of it we write as I, so the unbarred coordinate, and j, the index for the barred coordinate. Okay, note we have one superscript and one subscript. So each element is just dxi by dx bar j. Okay, if we think about the forward transformation, so this is the inverse transformation that we've thought about. If we now think about the forward transformation from the unbarred to the barred system, then if we do the same thing, we find that we need a different Jacobian matrix, and we call this one J bar. And this has a superscript I and a subscript j, and this is just, so the element of our J bar matrix is the inverse, so it's dx bar I by dxj. Okay, so the inverse transformation involves partial derivatives of the unbarred coordinate system with respect to the barred coordinates, and the forward transformation involves elements which are partial derivatives of the barred coordinate system with respect to the unbarred coordinates. Okay, so j takes us from barred to unbarred, and j bar takes us from the unbarred to the barred. Okay, so let's etch this into our minds. These guys will be your friends for the next few weeks, maybe throughout the whole course, and these will be popping up. These elements will be popping up everywhere, okay? Okay, so let's consider again the coordinate differential dxi, and we can write the chain rule for this. So this is sum over some index a, dxi by dx bar a, dx bar a. Okay, so this is the coordinate differential for the unbarred coordinate xi, given with the chain rule where x bar a is the coordinate in the barred system, and dx bar a is the coordinate differential in the barred system. So let's take a partial derivative. So we can have dxi by dxj, both unbarred coordinates, and this gives us the following. We get a dxi by dx bar a, and we get a dx bar a by dxj. But our coordinates are independent, so we know that this, the left-hand side, is a Kronecker delta, which is 1 or 0, so this is a unit matrix, effectively. On the right-hand side, we can see that this dxi by dx bar is just our matrix J. So this is J with elements I, A. And this guy is just our elements of J bar. So this is J bar, A, J. Okay, so we see that the matrix, okay, so if we forget about the summation, this is a matrix equation, effectively. This is J times, should be a bar, J bar. Okay, and that equals 1, a unit matrix. Thus, J bar is the inverse of J. Okay, so J and J bar these matrices are inverses of each other. Okay, as you should expect. So one takes us from the unbarred coordinates to the barred, and the other one takes us the other way. Okay, so we're going to have indices all over the place, so we want to make life easy for ourselves. So if we consider, for example, what we just saw before, where we had a sum over A of J, I, A, J bar, A, J, then we can use what is known as Einstein summation notation. And in the summation notation, basically we drop the sum, and any index that occurs exactly twice, so for instance here, the index A is appearing twice, one downstairs and one upstairs. If an index appears twice, one upstairs and one downstairs, then that implies a sum over that index, and we don't have to write the sum. So we can just as happily write this expression as J, I, A, J bar, A, J. Okay, and here the sum is implied. So this means this. Okay, and being able to drop all these summations, because we'll see we'll get quite a lot of them, saves time and effort. Okay, so that's the Einstein summation notation. The index that appears exactly twice, one downstairs and one upstairs, this is called a dummy index. So you can replace that with anything you like. So this can be written as J, I, anything you like. Okay, so let's have a cat, J, cat, bar J. Okay, so this thing is called a dummy index. So an index that appears exactly twice, one upstairs and one downstairs, is a dummy index. What I mean by upstairs, I just mean the superscript, and downstairs, I mean a subscript. The other indices are called free indices, so I and J. So this thing depends on the free indices I and J. Okay,